Hello and welcome to this video on what are degrees of freedom in confirmatory factor analysis and structural equation modeling. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate methods including factor analysis, structural equation modeling, multi-level analysis and latent class modeling. If this is something that interests you, please consider subscribing to this channel. Also, check out the description for additional resources, including workshops that I offer for QuantFish. In this video, I want to address the issue of degrees of freedom in factor analysis and structural equation modeling, and specifically I want to talk about what degrees of freedom represent, how do we interpret those, what are they good for, and then also I want to show you how you can calculate them by hand based on an example. So what are degrees of freedom? You could think of degrees of freedom in terms of ways in which a given CFA or SEM model may be wrong. So basically they quantify the number of times or the number of instances in a model where this model could be falsified. Or we could say each degree of freedom represents a testable restriction for either the mean structure of the observed variables or the covariance structure of the observed variables. So for example, a model may imply that two of the observed variables have equal variances in the population. And then that could result in a degree of freedom. Or there could be a restriction with regard to the mean structure, such that, for example, the means of two variables have to be equal in the population as implied by the model. And then this yields degrees of freedom that can be used for a model fit test, as we will see later. So how do we calculate the degrees of freedom? How can we find out how many restrictions there are in a given model? In general, degrees of freedom are calculated as the number of pieces of information minus the number of freely estimated model parameters. So it's as simple as that. However, then what is not so simple and often confusing for people is where do we find the pieces of information? So how do we count those? And then also, what are the free model parameters? Where do we find those? How can we figure out how many free parameters there are in a given model? And so I want to make this clearer by showing you an example. And so we're going to start with the number of pieces of information, which I abbreviate here with INF. So in general, what can we use as pieces of information when we estimate the parameters of a confirmatory factor analysis or a structural equation model? First of all, there are means in the observed data. In my example here, I have 4 observed variables or indicators, y1 through y4, and obviously each one of those indicators has a mean in the sample. So there's a sample mean that I can calculate, and here I calculated it with the Mplus software program that can be used for CFA and SEM, and I found those observed means. So those are part of the set of information, or the mean vector is one aspect here that can be used for each variable. There's one mean and each mean counts as one piece of information. Furthermore, there is the covariance matrix of the observed variables. And the covariance matrix is usually the main focus of our CFA and SEM models. When we have cross-sectional single group data, usually the mean structure is not that interesting. And as we will see later, oftentimes it is simply used as a saturated structure in a CFA or SEM, meaning no restrictions are placed on the mean structure, and it's not that interesting when you have cross-sectional single group data. However, when you have longitudinal data, repeated measures data, or you have multi-group data, then you also might place restrictions on the mean structure, and the mean structure may be more relevant because then you might be interested in mean changes across time and or mean differences across groups in a multi-group design. So when you have cross-sectional data, more of the focus of the model is typically on the covariance matrix, which you can see here at the bottom. And the covariance matrix actually contains both covariances between the variables and also the variances. In the main diagonal of the covariance matrix, so here where you find the 7.487, the 5.904, 3.781, and 3.806, those are the covariances of the variables with themselves. And a covariance of a variable with itself is equal to that variable's variance. So this means in the main diagonal of this matrix, we find the variances. And then off diagonal are the covariances. So with 4 variables, we have 4 variances because each variable has a variance. And then there are 6 covariances, as you can see here easily from this matrix. So this means that when we have 4 variables in our SEM or CFA model, there are 4 means plus 4 variances plus 6 covariances equals 14 pieces of information. So that's pretty easy to see. However, when you have a larger model with more variables, then it becomes tedious to calculate all those pieces of information by hand. And so instead of doing that, you can use a formula that gives you the result for any number of observed variables. In this formula, M indicates the number of variables, in our case 4. And so then with the formula, or the formula says that there are M plus M times M plus 1 divided by 2 pieces of information total for a set of M variables. And that's because there are M means, so that's the M plus before the fraction, and then the fraction itself represents the variances and covariances. In our example, we have 4 variables, so we have 4 plus 4 times 4 plus 1 is 5 divided by 2 would be 10, so 4 plus 10 is 14 pieces of information that we can use. And that is fixed. So say for a given number of variables, regardless of which model you fit to these data, if you stick with those 4 variables, you would have 14 and only 14 pieces of information to work with, which means you could not fit more than 14 parameters. You couldn't have a model that uses more than 14 parameters because you only have 14 pieces of information that you can use. So at most 14 free parameters could be estimated. Now let's talk about the parameters next. And so what are the free parameters in CFA and SEM? And I'm going to begin with a structural equation model here, specifically with a latent regression analysis model for those 4 variables. You can see the 4 variables here, y1, y2, y3, and y4 are shown in boxes. Those are the latent variable indicators. And we have 2 factors, f1 and f2. f1 predicts factor f2 in a latent regression analysis. And there is a regression residual R2 that indicates variance in F2 that cannot be predicted in a linear regression of F2 on F1. So now what are the free parameters in this structural equation model? That's a little bit more tricky to figure out compared to the number of pieces of information, which are always given by that formula that I showed you on the previous slide. Unlike that formula for the pieces of information, there's no such formula that you can use for an SEM, because SEMs can look very different in structure, and so you have to figure it out yourself for each and every SEM. And so we have to think about the structure of the SEM. In the SEM, we have first of all a measurement model. The measurement model is the model that connects the observed variables and the latent factors. So here we have a general measurement equation for the measurement model that says yi, so a given indicator observed variable, is equal to an intercept alpha I, that's an additive constant, plus lambda I, that's a factor loading or multiplicative constant, times the given factor that this variable measures, fj, plus an error term epsilon I. And so I here stands for the observed variable and j stands for the factor. And so we have 4 such equations in this example model because there are 4 observed variables. And for each one, we have an intercept. So we have alpha 1, alpha 2, alpha 3, and alpha 4. And also for each one we have a factor loading lambda. However, not all of the lambdas are typically freely estimated, because for model identification, to set the metric or define the metric of the latent factor, typically one factor loading is fixed to 1. And many programs, including Mplus, do this by default. They use the first indicator by default and fix that indicator's loading to 1 on each factor for model identification. And so this means the factor loading lambda 1 for y1 and the factor loading lambda 3 for y3 are not free parameters. They are not estimated because they are fixed to 1 in this example. And therefore they do not count as free model parameters. So that's important. Another parameter that we have in the measurement model, other than the constants alpha and lambda, are the variances of the error variables epsilon. So for each variable there's a measurement error variance, var epsilon I, and so 4 of those are being estimated here, and those are all free parameters. Furthermore, we have a structural model in this latent regression, and the structural model here is also a regression that is given as f2 equals beta 2 times f1 plus residual r2. So that's the latent regression where f2 is regressed on factor f1 with a beta regression or path coefficient for the linear regression plus a regression residual. And so in this regression then, the beta is a free parameter, and the variance of the exogenous variable, the variable that serves as independent or predictor variable, and also the variance of the residual. And that is a frequent source of confusion because many people think, oh, maybe we should estimate the variance of f2. However, since f2 is an endogenous variable here, a dependent variable that is predicted by another variable in the model, we're not estimating f2's variance. Instead, we're estimating the residual variance for that factor, and because the variance of f2 is a factor or is a function of beta, the variance of f1 and the residual variance. And so therefore the variance of f2 itself is not a free model parameter. It is determined by other model parameters. So those are the parameters that we would estimate in an SEM. For exogenous variables, we estimate the variance. For endogenous variables, we estimate the residual variance, and then path coefficients are estimated, as well as factor loadings, intercepts, and error variances. Now, one thing that you might ask is, why is there not an additive constant in the structural regression model? So why is there not a beta 0 in the equation f2 equals beta 2 times f1 plus r2? And the reason that there's not an additive constant or intercept in the structural equation is that there's no mean structure here included for the latent variables. And that's because the mean structure is arbitrary in a structural equation model in most cases, and it's not of interest unless you have a multi-group analysis where you compare different groups, or if you have a longitudinal study where you compare means across time. And so therefore the mean structure of the latent variables is often left out, or we could say the latent variables are centered. They are mean centered, assuming their means are 0. And so means are then only relevant for the observed variables, and they are used for estimating the intercepts, alpha 1, alpha 2, alpha 3, and alpha 4, which means the intercepts in many cross-sectional single group structural equation and factor models simply represent the observed means. There are no latent means included, and therefore also no intercepts in the structural models. Now let's count the number of free parameters that we have here. We have 2 freely estimated factor loadings. We have 4 intercepts. We have 4 error variances. We have our beta structural path coefficient. We have the variance of f1, and we have the variance of the residual r2. And so in total, we have 13 free parameters in this SEM. Now, Let's turn to CFA. What does this look like in a confirmatory factor analysis? And I'm going to use one for the same data example. So now we have, instead of predicting F2 from F1, simply a covariance between F1 and F2 in a confirmatory factor analysis model. We don't estimate structural path coefficients, but instead we may or may not allow covariances between our latent factor. So what does this change in terms of our count of the free parameters of this model? First of all, this measurement equation does not change. So we have the exact same measurement model as in the previous latent regression SEM model. That does not change at all. So we again have our 4 intercepts, we have our 2 loadings that are freely estimated, and we have our 4 error or residual variances in the measurement model. So the exact same parameters as before. What does it look like for the structural part of the model, or the latent variable part of the model? In the latent variable part of the model, we again estimate the variance of F1 because that's again an exogenous or independent variable. And now F2 is also an exogenous or independent variable. It's no longer predicted by F1, and therefore now also the variance of F2 is estimated rather than a residual variance. There's not a residual term here in the structural model. And then instead of estimating the beta 2 path coefficient between F1 and F2, we're now estimating the covariance between F1 and F2. And so that still yields 3 parameters in the structural model. Remember, previously we had the variance of F1, the residual variance of R2, and the beta in the structural model. And now we have 2 variances and the covariance. So that doesn't change anything. The model still has 13 free parameters as the previous model. And in fact, the SEM that I showed you on the previous slide and the CFA are equivalent models. They fit the same data equally well. They produce the same degrees of freedom and the same chi-square fit statistic. So those would be equivalent models. Now, how do we get to the degrees of freedom in our examples? We have seen previously that there were 14 pieces of information, 4 means, 4 variances, and 6 covariances in the observed data. And we subtract the 13 free parameters in either model from those 14 pieces of information, which yields 1 degree of freedom. This means this particular model has 1 testable restriction, and this can be tested with a chi-square test of model fit. So I fit this model here in Mplus, and I got this chi-square test of model fit with a value of 0.514 for the test statistic, 1 degree of freedom, as you can see here, and a p-value of 0.4736, which means this model is not rejected. So a non-significant chi-square statistic indicates that the model fits the data adequately. The null hypothesis of exact model fit does not have to be rejected, and therefore this model has adequate fit. Now, what is being tested here? What's being tested here is a complex constraint with regard to the ratio of observed covariances in the data that yields 1 degree of freedom. So this is a model that is over-identified, as we say. It is testable, has 1 degree of freedom, so it could be falsified if that constraint with regard to the ratio of the covariances were incorrect. Then the model may be rejected by the chi-square test. Now, having positive degrees of freedom is a necessary condition for over-identification. So whenever you have more than 0 degrees of freedom, then this can mean that your model may be over-identified and testable. Unfortunately, it's not a sufficient condition for over-identification because there are models that have positive degrees of freedom and they're still not identified. So unfortunately, it's not a safe thing to look at only the degrees of freedom for model identification, but at least it's a necessary condition, so to say. When you have positive degrees of freedom. What if you had 0 degrees of freedom? A model with 0 degrees of freedom is called a saturated model. And I have a separate video on or more than one, I think, on saturated models here on this channel that you can check out. And saturated simply means that all the information in your data is being used to estimate parameters. Everything, so to say, is consumed. And then there are no testable restrictions in the model. There's nothing that can be tested. Everything is being used. It's not necessarily bad, because a lot of models that we fit in practice in statistics are saturated, such as regression models, for example. Multiple regression models are always saturated, and yet they can yield useful parameter estimates nonetheless. Really problematic is when you have less than 0 degrees of freedom. So when your degrees of freedom are negative, then you know for sure that your model cannot be identified. Then you have an under-identified model. You have an identification problem for sure with negative degrees of freedom. You cannot estimate more parameters than you have pieces of information in your data. Then you would have to reduce the number of parameters either by adding more variables or by including additional constraints, additional restrictions that reduce the number of free parameters in your model. I hope you found this video useful to learn more about degrees of freedom in factor analysis and SEM. If you did, please hit the like button, consider subscribing to this channel, and don't forget to check out the description for additional resources, and I'll see you next time.